Problem number 15. An upright rod of length L is launched into the air with a vertical velocity Vy. It is given enough angular momentum so that the rod rotates by an angle of 2 pi before landing. Find the initial horizontal velocity of the bottom of the rod. Solution for problem number 15. If this rod rotates by angle 2 pi during this time, we can count this time to travel, and this time will be period of rotation. And this is the formula how to count this period. That's 2 Vy over g. Now we can count what is angular velocity of this rod, omega. It will be 2 pi over period t, which is pi g over Vy. And the last step to find what is horizontal velocity of the bottom end of this rod. That will be omega multiplied by radius, which is L over 2. And the final result for horizontal velocity is pi over 2 GL over Vy, which is answer B. And that was solution for problem number 15. Problem number 16. The depth of a well D is measured by dropping a stone into it and measuring this time t until the splash is heard at the bottom. What is the smallest value of D for which ignoring the time for the sound to travel gives less than a 5% error in the depth measurement? The speed of sound in air is 330 meters per second. Solution for problem number 16. The time t for the rock to reach the bottom of the well is related to the depth d by formula d equal 1/2 gt square. The time delta t that it takes for the sound of the splash to reach the top of the well is delta t equal d over v, where v is the speed of the sound. If one uses the time t plus delta t to estimate the well depth, then one arrives at an estimate d plus delta d equal this expression. So we can count that delta d equal gt delta d. So when we divide this equation by first equation, we can find what is relative error for d measurement. That will be delta d over d equal 2 times delta t over t. And now we can express time t from first equation and delta t from second equation. So we have t equal square root from 2d over g, and finally we get delta d over d equal this expression, which is 0.05. And now from this equation we can find what is our distance d. That will be this expression, or after putting numbers we have approximately 14 meters, which is answer C. But the intention of the problem was to find a distance d such that the error due to sound propagation may be neglected and the word smallest should have been removed. Due to this confusion, and to give students credit for selecting A equal 3.5 meters, which is the smallest depth that satisfies the problem, both answers choices A and C are given full credit. That was a solution for problem number 16, where correct answers are C and A. Problems number 17 and 18. The following information applies to a questions 17 and 18. A launcher is designed to shoot objects horizontally across an ice rink. It consists of two boards of negligible mass connected via a spring-loaded hinge, which exerts a constant torque tau on each board to keep them together. For both problems, neglect friction with either the ice or the launch boards. Problem number 17. A hard disk is pushed into the launcher between the boards until the boards make contact with it, a distance L from the hinge, and are open to an angle theta as shown in the figure. What is the minimum force necessary to hold the disk in this position? Solution for problem number 17. Each board exerts a force with the magnitude F equal torque tau over L, directed toward the center of the disk. We can decompose these forces into a component parallel to the symmetry axis of the launcher. That will be F multiplied by sine theta over 2. And the perpendicular components from two forces cancelled, while the parallel components add together. So we have a minimum force required to keep the disk in place must equal the sum of the two parallel components, which give us this expression. This is the answer A, and that was a solution for problem number 17. Problem number 18. The disk is removed and replaced with the E-shaped wedge of the same mass m, so that the hinge is still initially held open at an angle theta, as shown in the following figure. If the wedge is released from rest, what is its speed after it exits the launcher? Solution for problem number 18. Because torque is constant, it means the total potential energy of this launcher is tau multiplied by theta, which is going to kinetic energy of this wedge. So we have equation tau theta equal 1/2 mv square. And from here we can find what is final speed. That will be expression v equal square root from 2 tau theta over m, which is answer D, and this is the solution for problem number 18.